Here we see another feedback circuit. So the first step is identify the type of feedback by looking at the input source and the output source. So here, input is voltage, output is voltage, so it's going to be a series shunt type network. And then identify the feedback portion where you look at the output. Here I have connected at the output RL, which is not going to be part of the feedback. I have 1 milliamp, which is going to bias this transistor. Without it, it's not going to be biased. So I have to include that there. So I have, as part of my feedback portion, this 1K and 100K. So from that, I want to find R11, R22, and beta. So I redraw this feedback portion, and I look in on this side for R11, and I have to look at where it connects on this side, which is here at this location. So I look at what's on that side. It's a shunt, so I short this. If it was series on this side, I would leave it open, and I have 1K is my value for R11. For R22, I draw the same network, and I look in here for R22, and I look on this side, and it's series on that side, so I leave it open. It's a floating resistor, so it does not factor in the actual value, and this is going to be then 100K. So these are located on this small signal drawing. The input side is located here, so I place at that same location on the small signal R11, which is a value of 1K. On here, I look at the same location over here, which is located here. In the small signal that I drew, it was said that all current sources have 200K output resistance. So wherever these current sources were, I placed the 200K and the 200K for both of those. So this is next to that, and this is going to be the value of 100K. The last thing that I need to find from the feedback portion is beta feedback. So I use the same network. I look at the output type, which is a voltage, so I place V0 here. The input is also a voltage, so I place from where it connects the positive, and I refer to ground as VF, and beta is going to be VF over V0. So I see that this is floating, so no current is going to flow there, and beta feed, which is going to be my feedback beta, is VF over V0. So I need to find an equation with V0 in terms of VF. Well, I see that without any current flow there, this is the same wire. So V0 equals VF, and then I divide by this, and I get that this is equal to 1. So beta feedback is a value of 1. So now that I have my small signal model, I want to let you recall that for a PNP, this was a PNP transistor instead of an NPN. I have the model for a PNP, the small signal, recall, can be written looking like this. So this is my base, this is my emitter, and then this goes from collector to emitter GM Vpi. So using that, I placed that same one here so that it was easier to analyze this circuit. So now that I have my small signal, I need to get 3 pieces of information from this. I need, right here, SeriesShunt. I need to get A, which in this case will be V naught over Vs. And I need to get Ri with Rs in it. And I need to get Ro with Rl in it. So Ri including Rs will be located at this place, and R including Rl will be located at this location. So first let me find A. So looking here, I have a current going up, and then I have these three resistors can be written in terms of 1. So I can say that V naught is equal to minus GM V pi, all three of those in parallel. Then I need to get a value for V pi. So plugging in, this is V2. I'm given GM2 and GM1 and the DC values, so I can plug those values in here. And this gives me a value of V naught is a minus 77.68 V pi 2. And V pi 2 I can write as a minus GM1 V pi 1 or VGS1 multiplied by 200K in parallel with R pi 2. And R pi 2 is beta over GM2. Remember, this beta is 100. It's not beta feedback, so make sure to keep those straight. And plugging that in, I get that V pi 2 is equal to a minus 2 milli 2469 VGS1. So now looking at VGS1, which is here, is going to be a voltage divider. So VGS1 is equal to Vs 1K over 6K. And then I can plug those into each other. So plug VGS1 in here, V pi 2 back into here, and I can get V naught over Vs, which is what I want for A. And that gives me an end value of approximately 64 volts per volt. So this is only my open loop value though. So this is called the new A circuit, and it's not the feedback values. So you use these values to get the feedback values. So AF will be equal to A over 1 plus A beta feed. So 64 over 1 plus 64 times 1. So this is equal to 0.98 volts per volt. So this is my actual feedback value. Ri will include Rs. So this will be 6K for Ri. RIF, which also includes Rs, is determined by whether it's a series shunt on this side. It's a series on this side, so I multiply by the feedback amount of feedback. So this will be 390K. So now this is with Rs in it. Without Rs, which is called Rn, will be RIF, and because it's a series, I just subtract off Rs. So my Rn will actually be 390K minus 5K. So it will be 385K. So my actual values, I'm going to just note them down here as I go. A was 64. AF is 0.98. Those are volts per volts. RI F is 390K, and RN is 385K. So these are the values you actually are going to use. And the last one was RI or RO. RO so I erased it, was on the collector side of the BJT, and it had all three of those in parallel. So it was RL, the 200K from the current source, and then R22, which was 100K. So all three of those was RO. And that was a value of 1,942. And ROF is on this side a shunt, so you have to divide by the amount of feedback. So that's approximately 30 ohms. This includes, though, RL. To remove RL to get R out, this is a shunt, which means it's in parallel, so I have to take 1 over ROF minus 1 over RL to get the actual value for R out.